Hello, welcome once again to our YouTube channel. Today, we want to find the value of x, given that you have 1 to the power of x equals 2. So now, let's see how to solve it. Now, from here, we have 1 to the power of x equals 2. Though this problem is a little bit difficult, and some people may say that it doesn't have real solution. But before that, let's verify whether it has real solution or not. But it's sure that this problem has complex solution. Now, before that, let's introduce natural log to both sides. When we introduce natural log to both sides, we have here to be ln of 1 to the power of s equals ln of 2. So from here, this will come here, we have x ln of 1 equals ln of 2. Now, by dividing through by ln of 1, divide this one by ln of what? 1. This will cancel this. So we have our x to be equals ln of 2 divided by ln of 1. But mind you that this will give us a constant, but this one is equivalent to 0. And because the natural log of 1 is equal to 0, and that is why this implies that it has no real solution. But recall that this problem have a complex solution, and to solve for the complex solution, let us recall from what we call Euler's formula. Now, if you want to introduce Euler formula is given as e to the power of I theta equals cos theta plus I sin theta. This one indicates the real part, this one indicates the complex parts. Now, first, let's test. When theta equals 0, let us test if this condition will satisfy. I mean, the left hand side and the right hand side. If theta equals 0, let's see what will happen here. Are we going to have the same thing? So from here, we have here to be e to the power of I multiplied by 0 equals cos 0 plus I sin 0. So from here, we have e to the power of 0 equals cos 0 will give us 1 plus sin 0 will give us 0. Now from here, you have e to the power of 0 will always give us 1, and here we also have here to be 1. So this is true for theta equals 0. Now, if we set our theta to be equal to k pi, such that our k is a member of integer, the positive integer, k equals 1, 2, 3. Now, let us now see what will happen. We have to recall from Euler's formula that e to the power of I theta equals cos theta plus I sin theta. Now from here, when theta equals 2k pi, such that k is a member of positive integer, k, that is k equals 1, 2, 3 to positive infinity. Now we have e to the power of 2k pi I equals cos 2k pi plus I sine 2k pi. So therefore, from here, we have this as this. Okay, let us now test for the k. When k equals 1, what are we going to have here will be e to the power of 2 pi I equals, cos from here 2 pi plus I sine 2 pi. Now, we have e to the power of 2 pi I equals, cos 2 pi will give us 1 plus I sine 2 pi will give us 0, and this equals 1. E to the power of 2 pi I equals 1. Okay, when k equals 1, we have this. So also let us check. When k equals 2, we have e to the power of 2 k pi I that equals cos of 2k pi plus I sine 2k pi. Then when k equals 2, so from here we have e to the power of 4 pi I equals cos of 4 pi plus I sine 4 pi. So from here we have e to the power of 4 pi I equals cos 4 pi equals 1 plus I sine 4 pi equals 0. This also gives us 1. So when k equals 3, from here we have e to the power of 6 pi I equals cos 6 pi plus I sine 6 pi. So which implies that we have e to the power of 6 pi I equals, from here this cos 6 pi will also give us 1 plus I multiplied by sine 6 pi will give us 0. This also equals 1. You can see what will happen now. We have e to the power of 4 pi I equals 1. E to the power of 6 pi I equals 1. And likewise, also when you recall, we have e to the power of 2 pi I to be equals 1 as well. So therefore, generally, we can have it to be e to the power of 2k pi I that equals cos 2 pi plus I sine 2 pi always give us what? 1. This always give us 1. So now we can now do something reasonable. Let us recall from the problem given to us, because we want to make use of this Euler expression. Since we have proven this expression to be equals 1, let us recall from where we have 1 to the power of s equals 2. When 1 to the power of s equals 2, we can simply substitute this one as this, because it's equivalent to 1. So we have here to be e to the power of 2k pi I out to the power of s equals 2. And so from here, guys, we also have this one to be e to the power of 2k pi xi to be equals to. Now, we want to make sure that we have this as the base. We can introduce natural log ln of e to the power of 2k 2 pi k xi equals ln of 2. So when this cancels this, we have 2 pi kxi to be equals ln 2, And obviously we can divide 2 by 2k pi I divided by 2k pi I. So this we cancel this, and this we have our s to be equals ln2 divided by 2k pi I. And that is the final answer for the value of x. If you are new here and you find this video interesting, don't forget to share, like, comment, and subscribe to my YouTube channel for more mathematics tutorial videos. So to check, you can easily check. So when 1 to the power of s equals this, remember that 1 equals this one. When you substitute it here, and our s equals this, so we have it to be 2k pi I, then is it going to give us 2? Now from here, you see, this we cancel this. We have e to the power of ln2, and it's going to give us 2. This we cancel this, so we have 2 to be equals 2. So this is true. Bye bye.